So it's a pleasure to be here. Today I'm going to be talking a little bit about agent-based modeling, artificial intelligence, and applying that to autonomous vehicles and understanding autonomous vehicles. And I think what's interesting is that the tools that we've used to understand our reality have forced us to pretend that the world is linear, that we act rationally, and that everything around us is homogeneous. And we've had to make those simplifying assumptions just to make the mathematics tractable. And as a result, the predictions that we've made tend to be very linear. We take a lot of data points on the past, and effectively we do advanced curve fitting. And if you look at things like trip planning or the allocation of resources for autonomous vehicles or for taxis, they rely on very simple equilibrium models, such as shortest path algorithms, or maybe some more advanced heuristic-based search options like that can incorporate travel choice, demand, real-time traffic, and so forth. But all of these approaches, these two approaches I mentioned and many others, they sort of aim for an equilibrium, okay? And they have to make these really gross simplifications as to the nature of reality to make the maths easy for us and to minimize the computational requirements to solve the equations. But the reality is that the world that we're in is not simple. It's not linear. It's made up of something called complex adaptive systems. And there's sort of 4 points that I want to talk about with respect to transportation systems that make these traditional equilibrium models unreliable in the 21st century. So I think the first one is this idea of delays. So critical factors in our transportation systems accumulate over very long periods, and they cause delays between action and results. And when you don't acknowledge these delays, it can create severe and undesirable long-term consequences. Just think of pollution as an example. Another important idea is this idea of interdependency. Just because, I mean, if you've experienced the traffic here, just because you build more roads doesn't mean that travel times will improve. And that's because of all of these interdependencies in our road networks that you have to get multiple choices right on multiple issues. Another important point in these complex adaptive systems is our understanding that many feedback mechanisms exist. And these can accelerate change, both good and bad, or else cause improvements to stall or backfire. And you have to get multiple competing feedback loops working right. And if you don't, they can frustrate our best efforts. Think about trying to address congestion by building more roads. It doesn't work because reinforcing and balancing feedback loops cancel each other out with a delay. And this creates an irritating oscillatory behavior that frustrates us and makes us hate our politicians. And I think another important thing is this idea of thresholds. Good things happen, or good things don't seem to happen until you reach a tipping point, and then all of a sudden everything takes off. Or bad things happen when you hit the tipping point. So for example, congestion. Actually, some congestion is good. It's an indicator of higher productivity and growth. But above a certain threshold, it's actually a drag on economic growth. So these are some important points about complex adaptive systems. And if we take this sort of a simple example of a few cars driving around in a circle, this is a very well-known example from the literature. And this idea of if you put a bunch of people, like say 20 cars, in a circle, you put a person in the car and you have them drive, what happens? Well, you would think that they could just drive around without causing congestion. But in the absence of any exogenous shock, there's no accident, nothing happens, you actually see congestion building up in this little tiny simulation of what it's like to drive in a real world. Okay? And this is fascinating. This is the Mathematical Society of Traffic Flow. This is many years old. And what is causing that? What's causing this? Us. We're the cause of these congestions. All too often, if you've ever been on the road, and there's no accident, and yet you have all this congestion. And it's subtle micro movements that we're making as individuals that when you accumulate them, it creates this sort of congestion and problems. But within 10 years, the vast majority of vehicles are going to be fully autonomous. And this has profound implications for road safety, for all sorts of different things. And as these vehicles travel around the cities and our communities, they will be in constant communication and they'll be sharing all of this information amongst themselves and with the city. And what this means is that we can use this data to do some really important things. We can reduce fuel. So when the robots are driving the vehicles, they can drive more efficiently than we do, okay? So no more stop and start, no more pretending you're a race car driver, okay? The robots will drive you safely and efficiently. And then also, of course, we're moving to more electric vehicles, and that's also going to have an impact on fuel consumption. Autonomous vehicles will be safer than humans, okay? That means that the roads will be safer, okay? Statistically speaking, driving is one of the most dangerous. When I used to work in Baghdad, my mother would always say to me, be careful, don't die. I said, I'm more worried about the drive around Baghdad than I am being killed in a car accident than I am being killed by a terrorist or being attacked. And the other interesting thing about these things is that it can reduce congestion. So I'm going to talk a little bit about how you do that at a city-wide scale. Once you have autonomous vehicles and they're all connected together and they're sharing data, then the city can get a city-wide view of all of the vehicles. And the city operating system can then start to manage the autonomous vehicles to achieve multiple objectives simultaneously. So I want to talk about a real project that we're working on, that one of our clients is working on, which is simulating all of the traffic and all of the vehicles in London. Now, all of the code for everything that I'm showing today is available. So if you go to our website and you sign up for our documentation, you can log in and get all the algorithms, all the code, and recreate all of this for yourself for London. Now, London is interesting because it has about 2.5 million vehicles. And over time, they'll be generating something on the order of 25 gigabytes of data per car per hour. Now, the challenge with AI is how do you manage all of these vehicles so that you can optimize the routing of all of the vehicles to achieve multiple objectives. So you want to be able to have the vehicles get to passengers that want to take the vehicles and go somewhere, but you also want to minimize congestion on certain roads. You want to take account into things like weather and also things like, you know, if there's an accident, maybe something in the natural world happens, a tree falls over a road or something like that, you need to be able to quickly and in real time adapt. And keeping track of 2.5 million cars and this much data is incredibly difficult. So the question becomes is how do you actually crack that? And the way that you do it is with something called distributed agent-based modeling with reinforcement learning. Reinforcement learning is one of the classes of artificial intelligence that many people have heard about. Now that's a mouthful, so I like to call these artificially intelligent simulations. And it's these artificially intelligent simulations, these AIs, that are going to help us manage the 21st century and to navigate it safely and confidently. So this is where you can, this is the simulation, so you can log on and get the code and run it for yourself. And it's a massive simulation. We can track billions of moving parts. That's people, vehicles, pretty much everything. And there's sort of 5 key points that I want to make about this particular simulation. So what we're doing is we're taking live data from vehicles and we're intelligently routing the vehicles to optimize multiple criteria: fuel consumption, travel time, congestion, and so on. The other thing that it has to do is it has to react in real time to changing circumstances in the system. So like that tree in the road, or spikes in demand, or road closures, accidents, and so on. The third thing that you want to be able to do is you want to optimize beyond the present and into the future state of the city and the system. You want to be able to have idle vehicles being dispatched to the areas where you're likely to have the passengers soon, okay? So this is getting rid of parking lots in the future. The vehicles will just sort of anticipate and be there when you need them. But you also need to ensure that if there's less busy times, that you've got them in the other spots where they need to be as well. For cities, okay, the ability to actually optimize fleet management. Okay, so request assignment. So how many vehicles do we need in our city? Okay, so what about this tension between services like Uber, where you have manned people driving it, but when they become autonomous, when these vehicles are driving, what's the right mix from these private vehicle services like Uber versus managing things like buses and this multiple passenger type of autonomous vehicles? What's that right balance? So enabling cities to be able to simulate and manage that balance. And I think also another interesting thing about simulation is it allows you to simulate the transition from manned people driving their vehicles to entirely and fully autonomous vehicles and what happens there. So how do we do this? So Simudyne, which is the company I helped to start, has built tools that make building these types of massive simulations trivial. Okay? And I'm going to talk a little bit about this. They can allow you to use any modeling paradigm. So if you're going to model a complex system, okay, like a city or like autonomous vehicles, millions of vehicles moving around, you need to use these mathematical techniques: agent-based modeling, discrete event simulation, as well as system dynamics. And these simulation techniques, when combined together, give you unprecedented ability to manage these complex systems. But the challenge with all of these simulations is that they're computationally very expensive. So you need to be able to scale them from 10 machines to 10,000 machines to make the math tractable. What I like to joke is we can search the entire internet for information in the blink of an eye. We should be able to ask questions of our computers and instantaneously get a response back as to how do I get my vehicles organized across my city. So the software that we've built is called Providence. And there's only one point I'm going to make on this slide that's really important, which is that we're leveraging something called Hadoop, which is a big data technology, an ecosystem of big data technologies that we're leveraging to get the kind of scale. And we're the only simulation platform that's been certified to run on Cloudera's distribution of Hadoop. So the software, we call it, is Providence. And I want to take you under the hood of how we're doing this and how we're connecting these reinforcement learning algorithms to these massive agent-based models. Now, the first thing that we need to deal with are these three layers. The data, remember, it's 25 gigabytes of data per hour per car. The models, all these different agent-based models of the city and all the vehicles and how we keep track of it. And then how do we bring it all to life so that our policymakers and we can understand it? So data is the first component. So these vehicles are generating vast amounts of data, sensor data, from a telematics types devices, LiDAR data, all sorts of data that's both structured and unstructured. And you need to be able to capture all of that data and use it. So that's interesting, and that's the idea of these data lakes. The next thing that you need to build is the concept of a model lake. So once you have these simulations running, you're building models, okay? And the models can either be built by the machines, where you take lots of data, you run it through an algorithm, and then you get a model of how the system works, machine learning. Or you can use human-based models. And human-based models are these types of models like agent-based modeling that I mentioned earlier, and combining that with network modeling. So it's these three things that when you weave these three things together that allow you to get predictive models that the artificial intelligence can then use to figure out how to manage the city for you. I'll come to that in a little bit. And the last component, and we learned this in our work with the Department of Defense and our work in Iraq. If you read the Wired article about our work with counterinsurgencies, we ran into real problems because the policymakers would not listen to the advice, let alone allow the AI to make the decision, if they couldn't understand what was happening and to visualize the results. So this ability to connect a web UI using HTML5 technologies to 10,000 machines behind the curtain, to be able to run the computations and instantly get the results back in a web browser on an iPad or a Surface Pro. This is incredibly hard to do, but getting it right is absolutely essential. So this idea of visualization. But the question then becomes is how do these simulations of all these autonomous vehicles interact with the real world? What's the connection between this real world that's happening, right, where real accidents are occurring, and this simulation world, which is mirroring the real world, but it's constantly being fed new data? And it's this feedback loop between the real world and the simulated world that allows us to introduce artificial intelligence. And the idea is that artificial intelligence, when combined with human beings, allows us to amplify our capabilities to make better decisions. Let me give you a concrete example. Chess or Go. Go is a game. Now, if you want to be a world-class Go player, you have to spend tens of thousands of hours playing the game over and over again. Now, your friends get really bored, right, playing the game with you all the time, so you end up playing simulations, computer versions of the game. Now, once you have a simulation of the game of Go, then you can attach a reinforcement learning or deep convoluted neural network to this simulation, and then it will play that game millions or trillions of times. And all you have to do is feed it electricity, and very soon it'll be better than the best of us. So what I tell people is that in the short term, absolutely the management of our cities will still have mayors. They'll still help make decisions, but they'll be using these computers to help them make the right decisions. And very soon we won't need the mayors anymore. The computers will be taking over and making those decisions for us and helping us live a much better life. So what are the types of AI algorithms that we can use? So I think one of them is this idea of, let me just go back one slide, I went too forward. Q-learning. So Q-learning, for whatever reason, it's skipping the slide. Q-learning is a way, it's a reinforcement learning algorithm. Unfortunately, I can't go through the equation. But what it does is it strikes a balance between exploration and exploitation. So is anyone here familiar with Q-learning? So Q-learning is this idea that you embed into each one of these agents a reinforcement learning algorithm. And what it does is the algorithm, the autonomous vehicle sort of explores its area. And as it explores the area, it learns about what's happening. And then over a period of time, through a specific strategy called decreasing epsilon, it figures out and starts to exploit what it's learned. It's very similar to what it's like to be a child, to explore our environment. We learn, and then we take that knowledge, and as we get older, we start to exploit that knowledge to achieve our desired outcome. Now, the problem with Q-learning is that it's a local, it's very specific to that one particular vehicle. So the challenge then becomes, well, how do I extend this? Because what if I'm trying to optimize and manage an entire city? I've got 2.6 million vehicles. They're generating vast amounts of data. I need to be able to distribute that as a graph across the whole clusters of machines. I need to be able to simulate those interactions. And then I need to be able to have a solver agent, some sort of a meta agent that exists above them all these individual agents that looks to optimize the entire city. Because what we don't want to do is have everyone acting rationally, all these little intelligent autonomous agents trying to optimize their own local thing, and then have what emerges out of this is a mess. Okay, that's what happens currently. Right? So it's an unintended consequence. It's an emergent phenomenon of these complex adaptive systems. So you need to combine these sort of simple Q-learning algorithms with other types of advancements in Q-learning, like the quicker algorithm. So the quicker algorithm is an extension of Q-learning, and it allows you to do an immediate counterfactual rewards learning. And this is very powerful for improving the overall management of the overall city. So those are two different things. This is, here's the Q-learning algorithm. This has been popularized. This is the foundation for what the guys, what we did with Demis. Some of those guys have done at DeepMind. So Q-learning is a reinforcement learning algorithm, and that's been extended into deep convoluted neural networks to do all sorts of interesting things. And the promise of these sort of reinforcement learning algorithms, coupled with some evolutionary computation algorithms, this is what promises to allow us to have all of these autonomous vehicles managing across the city. So at this point, I was going to open it up to any sort of questions if people have it, but that's basically what I say. I hope that you all found that interesting. It's been a pleasure being here. Does anyone do anyone have questions?
We have microphones. If you raise your hand, you will get a microphone and ask a question. Yes, we have one question here.
Hello. Thank you very much. It was
Pleasure.
really interesting. I heard about a similar simulation that was done in Moscow, and basically they simulated how people go to their workplace, and they realized that the model that they had in mind, that people live around the city and then all concentrate to go to a place, was wrong. And basically people were going in circles, in small circles, all around the city. So I wanted to ask you if there was any unexpected thing you found out by analyzing the traffic in London that you wouldn't expect.
That's a great question. So if everyone heard that, this idea of, so simulations are constantly surprising me with these sort of counterintuitive results. So the city of London simulation, I mean, if we look at the different research on it, there's been a lot of interesting feedback that's come out of it. How people are commuting in. So like the distances that people commute in is very surprising, but also the sheer number of people that do live in the city and take very small trips with vehicles. I think also one of the interesting things is the potential role that autonomous vehicles have for like ride sharing, that's a really complex mathematical model to try to figure out. Like, how do you have, so think of it as like a bus, but instead of the bus, perhaps following a set route, maybe the bus is actually tied to your mobile phones and is actually constantly readjusting where it needs to be based on its projections of where the people are going to be next. So it's like a little roving bus that says, basically the minute you think you need a bus, you look up and there's one there because it's sort of anticipated. So being able to simulate that, sort of to get that sort of foresight, I think is really compelling and interesting. The other thing that was really hard with the city is that it's just really complicated, the layout. Like getting it all integrated with OpenStreetMaps and being able to deal with all the different, like getting, it's really boring, but getting like the agents to move properly across the city landscape and deal with things like pedestrian crossings and one-way systems and that sort of thing was really hard. I think the next thing that I'd like to explore is a little bit around what's the role of congestion charging. So like as we transition to autonomous vehicles, do you ratchet up the congestion charging to try to get the people who drive, physically drive, to stop coming into the city? So it's just too bloody expensive. So these are the types of policy things that I think are the next sort of evolution of the simulation, to be able to test these policy interventions in a synthetic environment. All too often, our politicians, they say they do research, but they're just gut instinct people. And and you need to get beyond that and get into a fact-based decision-making cycle. Additional questions? In the back?
Yes. If you can state your name, the company you are representing, and your role. Thank you.
Hi.
Hello, how are you?
From Cloud Hero. So my question is, if your company is sharing data with the sorts of Uber, Lyft, or Waze?
So sharing data with Lyft and Uber. Well, Uber doesn't share data with anyone, so no. Trying to get cities to work with people like Uber is difficult. I mean, Uber and the city of London aren't getting along terribly well right now. Hopefully they'll sort it out. I think that in the future, when you look at this sort of existential threat that companies like Google and Uber face against people like Renault and Ford and so forth, it's quite existential for these organizations, because you can envision a world where you have these vehicles, instead of being driven by Uber drivers or Lyft drivers, they become fully autonomous, and you then see the ability for organizations who are building the software to power the autonomous vehicles to enter into the automotive space. So that's really stressful as well. So you see people like Ford. I think they made a $1 billion investment into an AI company recently. Other big automotive companies are also doing that as well. And the reason why is they want to try to own that city space. So they want to be able to deploy the software and the hardware, the vehicles, so that cities can manage it. So instead of having a bunch of like a private company managing all of this and letting go of this ability of the city to manage the transport needs of the city can still control that in collaboration with vehicle manufacturers. So in some cases they are exposing their data via API, but Uber doesn't. I think is there any time for one question, or is there?
Yeah, we have
more time. Okay.
Thank you. Ante from Here Technologies. I wanted to ask you, what kind of data the car produces? 25 gigabytes of data. What kind of data?
Sure.
And how important is the map for your computations?
So the question is, what type of data and how important are the maps? Well, the types of data would be everything from, things like what the tires are experiencing, the wear on the tires. It's your normal telematics devices. So there's hundreds of sensors in these vehicles, and they generate lots of data as the vehicle's going. And some of it's necessary for the immediate running of the vehicle. Other data is more useful for avoiding collisions, or basically being able to get a number of vehicles, like on the motorway, being able to chain together a number of vehicles. So moving beyond the LiDAR and basically trying to get behind other vehicles, but looking at more of a meta view outside of the sensor range to say, how do I string together a bunch of vehicles like lorries, for example, or how do I basically, reroute vehicles to avoid too much congestion in a particular part of the city. So the type of data would be like the LiDAR data, the sensor data from the vehicles. And the second question was around maps. So maps are absolutely essential. You can't do this stuff without really robust maps. You need the maps for all sorts of good reasons. So when you're training autonomous vehicles, everyone sees the vehicles on the roads driving around and learning that way. But you must know that the vast majority of the AI's learning happens in computer simulations. So if you visit the Google campus or you hang out with the guys at DeepMind or something like that, you'll see that they're building these massive simulations, okay? And they're using these massive simulations to train trillions and trillions of miles of driving for these autonomous vehicles in these synthetic environments, where it doesn't matter if you kill someone because it's just a virtual person. You just reset it. It doesn't matter. So these simulations, whether it's teaching them to play Go, or teaching them to drive, or teaching them to manage our economy or to set interest rates, that's the role of simulation with AI, and it's this linking together that's so important. So yeah, absolutely, the maps are critical because that gives you the realistic synthetic environment so the little computer can drive it. Another question?
So
Is that it? Time is up. Okay, thank you so much for your time. Appreciate it.